Hello, I'm Arjun, and Ayush and I will be presenting our work on improving vision and language navigation with image-text pairs from the web. This is joint work with Stefan, Peter, Davy, and Dhruv. In vision and language navigation, or VLN for short, we place an agent in a photorealistic environment, like the one you see here. Then, as shown at the top, we give the agent natural language navigation instructions that describe a path to a goal location. This video shows a path that enters the hallway, passes the banister rail, and then eventually ends up in the bedroom containing the round mirror and butterfly sculpture. Grounding these visual landmarks from the instructions is critical to solving this task. However, there's a long tail of these kinds of concepts that we might want our agents to recognize. For example, here's a histogram of nouns in the VLN training data. We see a long tail here, with the words to the right occurring only once. In prior work, VLN agents typically learn visual grounding primarily from this dataset. So if you want these agents to find the marshmallows, you're probably out of luck. The question is, how do we learn visual grounding for these types of rare concepts? Recently, there's been substantial progress in the vision and language communities on the problem of visual grounding in static images. This line of work has made use of transformer-like models and BERT-like pre-training objectives to learn visual grounding from large-scale web data. Here, we show an example of this paired image caption data, which was taken from the conceptual captions dataset. This raises our central research question. How do you transfer visual grounding from disembodied web data to embodied tasks like VLN? There are two key challenges with this kind of transfer. The first challenge is transferring visual grounding from static images to the sequential data that we must process in VLN. The second challenge is that there's a domain shift between the internet data shown on the top and the type of data collected by embodied agents, which is shown on the bottom. Typically, when an internet image caption mentions a couch, the couch is in full view. In contrast, in VLN, the viewpoints are determined by the navigation path, so agents need to recognize couches at these kind of skewed angles. In this work, we propose a model architecture and a training curriculum to address both of these challenges. Our model, denoted as VLN-BERT, is composed of the two stream structures shown here. Both streams are composed of BERT-like architectures and connected with cross-modal attention layers. The inputs to the language stream are word tokens taken from the navigation instructions. For the vision stream, we run an off-the-shelf object detector and treat the detected regions as visual tokens. Our paper includes additional details on the considerations we made for processing image regions from a sequence of panoramas. The output from our model is a score that measures the compatibility between the visual observations and the navigation instructions. We use this score to rank paths to solve a path selection task in VLN. VLN-BERT extends prior work in vision and language. We did this by design because it enables straightforward transfer from vision and language to vision and language navigation.
Hello, I am Ayush and I will first describe how we train VLN-BERT. In this work, we propose a three-stage pre-training curriculum where we first train on language data. This stage is equivalent to initializing the language stream with BERT weights. Next, we train on static image and caption pairs by initializing with weights from VLN-BERT. In this stage, our model learns to ground captions in static data. And finally, we train on sequential path instruction pairs from the VLN dataset. This stage adapts our model for sequential visual grounding. We perform stage-wise ablations and find that each of these stages add value. First, we find that the language-only pre-training in stage 1 improves performance over a no pre-training baseline. We also find that independently, stages 2 and 3 lead up to another 5 absolute percentage points of improvement. Finally, when we combine all three stages, we see further synergistic effects with another 9 absolute percentage points of improvement. Additionally, VLN-BERT's ensemble model performance improves substantially over the prior state of the art on the VLN leaderboard. The next two qualitative examples provide a feel for this improved performance. The navigation instructions describe a path that turns right, then left, then right, and eventually end up near an antelope head. The path selected by VLN-BERT is shown in blue and ends at the same goal location as the ground truth path shown in orange. So, in this example, there is no navigation error. We used a gradient-based technique to determine which regions VLN-BERT uses to select this path, and the top 5 regions are shown here. In this example, we see that VLN-BERT was able to correctly ground the phrase antelope head. This is neat because the word antelope appears only 3 times in the VLN training data, but 138 times in conceptual captions. So it is likely that the visual grounding was learned from there. In this example, we will compare VLN-BERT's visual grounding when we skip stage 2 of pre-training on image text pairs from the web. The key phrase in this set of instructions are the words mini fridge, which describe where the agent should stop. As in the previous example, the phrase mini fridge is only seen in the VLN training data once, so it is a difficult concept to learn. When VLN-BERT is trained without image text data, it is still able to ground common concepts like table, but it does not find the mini fridge and fails to correctly follow these instructions. In contrast, when we use our full training curriculum, VLN-BERT finds the mini fridge and is able to follow the instructions correctly. Thank you, and please see our paper for more details.